We want to differentiate trig functions then. I'm going to start off with some limits. So think of your sine curve. The limit as x approaches 0 would be 0. For cosine it would be 1, and our tan curve it would also be 0. Now I'm not going to use all of those limits, but one of those certainly is going to be very useful. That's a circle, in case you're wondering. Now, if I draw in a sector, and the angle at the centre I'm just calling x, and it's in radians. So it's x radians, and the radius is 1. Now what do I know about the area of that sector? Well, I know it would be greater than the area of that triangle I've just drawn in, OAC. Certainly would be greater than that. But it would be less than the area of this right-angled triangle. So AB is a tangent. Remember, we know a tangent's perpendicular to the radius. And I could work out using trig that AB would turn out to be whatever the tan of x happens to be. So let's work out the area of those three things. So the area of the first triangle is a half AB sine C. So in this case, 1 times 1 times sine x. Area of the sector, half r squared theta, in this case half 1 squared x, and the area of the right angled triangle, half base times height, so half of 1 times tan x. Well, we certainly can tidy that up. They're all times a half, so let's get rid of the halves. I end up with x is in between sine x and tan x. I'm going to divide everything by sine x. Now sine x, when you divide by sine x, well obviously tan x, when we divide it by sine x, we'd end up with 1 over cosine x. So I want to know what happens as x approaches 0. Now the left-hand side obviously stays as the number 1. The right-hand side, well remember we said the limit as x approaches 0 of cosine x is equal to 1. So we'd have 1 over 1, which is 1. So I've now trapped this expression, x over sine x, between 1 and 1. So I now know the limit. The limit as x approaches 0 of x on sine x is equal to 1. So if I had to do this one, limit as x approaches 0 of 5x on sine 5x, that'll be 1. The key is look at the angle. Now if x is approaching 0, 5x must be approaching 0 as well. The algebra on the other side of the fraction must match the angle, and in this case it does. 5x over sine 5x. Got that situation, you know the limit will be 1. So if I had this one, well, if x is approaching 0, 3x approaches 0, that bit's fine, but on the top I only have x. I need 3x. So I'll make it 3x and multiply by a third. The fraction I know approaches 1, therefore this whole thing approaches 1/3. That limit is going to become very handy in what I'm about to do. We want to know how to differentiate sine x. We go back to first principles. Let's create a formula. So sine x plus h minus sine x over h. Need to expand the sine x plus h. Sine cos cos sine. If it's the sine, it's the sine. I'm going to split that up. I've got cos x times sine h on h, but I've also got sine x times cos h minus 1 over h. Limit as h approaches 0. Well, that first fraction's okay. I've got the sine h on h. We now know that approaches 1. Cos h minus 1 on h, I need to do a bit of playing around. I can change that to 2 cos squared h on 2 minus 2. Basically, I've used my double angle result. Cos 2 theta is 2 cos squared theta minus 1. But in this case, theta is h on 2, because h is double h on 2. So I went 2 cos squared h on 2 minus 1, but then there was another minus 1 there already, so it became minus 2. Why do that? Well, because cos squared minus 1 is the negative of sine squared. So it now has become minus sine x times 2 sine squared h on 2 on h. I'm getting close to being able to use that limit. How about I rewrite it? 2 on h is the same as saying over h on 2. I've now got the angle matching what is underneath. Problem is I've got sine squared, not sine. So I'll rewrite that to say it's sine h on 2 over h on 2 times sine h on 2. I can now substitute in 0. The sine h on h, well that's approaching 1. The sine h on 2 on h on 2, that is approaching 1. And just sine h on 2 is approaching 0. So I'm left with cos x times 1 plus sine x times 0 cos x. So you differentiate sine, you get cosine. There's our derivation. Fortunately, we don't have to do that every time. Now we know that it's cosine. I can simply say, if I've got y equals the sine of some function, so it's the angle that we're differentiating, then I differentiate the angle, that goes out the front, and it becomes cosine function x. The angle does not change. Well, let's do cosine, and it's a lot quicker because now I know how to differentiate sine, and I can change cosine into sine. They're complementary ratios. So I can say, well, that's the sine of 90 minus x. And I now know how to differentiate that. Differentiate the angle, that's -1. It changes to cosine, the angle does not change. So I have minus the cosine of pi on 2 minus x. But cosine and sine, complementary ratios. So instead of writing cosine pi on 2 minus x, I'll make that sine. And that explains why when you differentiate cosine, it goes to minus sine, not just sine. So to generalize that one, if we've got a cosine function, then we differentiate the function, but it becomes minus the derivative times sine of function x. Let's have a go at tan. But I now know how to differentiate both sine and cosine. So if I rewrite tan as sine over cos, and I'll use the quotient rule, square the bottom. Write down the bottom, diff the top. The top is sine x. We now know sine x differentiates to get cosine x. Minus, write down the top, diff the bottom. The bottom is cosine x, but I now know when we differentiate that, it goes to minus sine x. Look what we get on top, that lovely expression. Cos squared x plus sine squared x, which we know is equal to, that's right, 1. 1 on cosine squared, well, the reciprocal of cosine is sec, and that's why we get sec squared when we differentiate tan. So to generalize that one, tan of some function, differentiate the angle, and multiply it by the sec squared of whatever that angle was. Okay, let's do some examples then. So sine of x cubed, differentiate the x cubed, 3x squared, the sine goes to cosine, the angle doesn't change. So 3x squared, the cosine of x cubed. Tan of 1 on x, all right? Differentiate the angle, differentiate 1 on x, we get minus 1 on x squared. Tan goes to sec squared, the angle doesn't change. So minus 1 on x squared, sec squared, 1 on x. The log of cos x. Okay, it's actually a log function we're differentiating here. So when we differentiated logs, it was derivative over function. Derivative, in this case, of cos x. So, derivative of cos x is minus sine x over the function, which is cos x. So we have minus sine x over cos x, which tidies up to be minus tan x. Tan x to the power of 5. So remember with trig, we put the power next to the ratio, but that's really saying tan x all to the power of 5. So we're going to use our chain rule. Anarchy. Bring down the power, 5. Lower the power, 4. Diff the inside. The inside is tan x. Differentiate tan x, you get sec squared x. So 5 tan to the power of 4x, sec squared x. Let's differentiate cos e to the power of x. We differentiate the angle, e to the x. Oh, it's an exponential. Differentiate e to the x, we get e to the x. But cosine goes to minus sine and the angle does not change. So minus e to the x, sine e to the x. Okay.